All right, class. I wanted to do an example for you where we do a Bernoulli equation solution with pumps. So here's the example. So what I have is I have two tanks here. This is our sort of prototypical pipeline example that we've been doing for several lectures now. And so what I'm going to do is I'm going to try to pump the fluid from tank 1 to tank 2. And I'm going to say that there's a change in height here between the level of the two pumps given by a delta Z with 4 meters. The pipe diameter here, so this will be my pipe diameter, is 1 meter, and we'll say that's the inner diameter. We've learned a little bit about pipes to know that we need to do the inner diameter. Note that this is an extremely large pipe. This is just picked for convenience and calculation. You really wouldn't hardly ever have a pipe that big. And we're going to assume that the length here of the pipeline is 200 meters. All right, and I'm going to assume also for convenience that I'm hydraulically smooth, that I have no minor losses, and that I have a constant friction factor, which we'll see will make the problem easy enough to solve by hand. And I can remove that assumption. I'll talk about that at the end of the video. So the pump has a performance curve given by this equation here. HP, which is the pump head, is given by H max minus BQ squared. So I said this in class. For an ideal pump, you get something that's linear. For a non-ideal pump, typically you'll write down a pump curve in terms of some constant minus some other constant times Q to the N. And this N's often 2, but it's whatever. This is just an empirical fit to the data. Here I've given H max, and then B is this value here, 0.05. H max is 13 meters. Okay, so that's our assumption. So how are we going to solve this problem? Well, we start out as we do in all of these cases, and we write down Bernoulli's equation, delta P over rho plus delta V squared over 2 plus G delta Z, and this is equal to the shaft work divided by W minus the viscous losses divided by W, or this is the mass flow rate. Okay, and this is the engineering Bernoulli equation. Excuse me, I said just Bernoulli earlier, but it's the engineering Bernoulli equation. Okay, and as we talked about in class, the more convenient form in this case is the head form. So I'm going to divide this entire equation by G. So I put a G, I cancel that guy, I put a G down here, and I put a G down here. And I said that this piece was the change in head of the pipeline of the system, and this here is my pump head, and these guys here are my head losses. So I can rewrite this equation as delta H equals HP minus HL. And it's more convenient to rewrite this a slightly different way, just rearrange and write this as the pump head is equal to the delta H of the system plus the head losses. And we call this the system demand. Here, the system demands this head, because this is what I need to overcome from my pressure and velocity and change in height. And then these head losses are what I need to overcome with my pump. And these two have to be equal. So what I'm going to find, and we'll see this in a minute, is that I'm going to put head as a function of Q, and I'm going to find my pump curve looks like this. This will be HP, and I'm going to find that my H system, H system is this guy, and what I want to find is the operating point. So I'm going to find Q operating, okay, and H operating. And that's going to be determined by where these two intersect. Okay, well, as a little review. So, but to set this up, of course, I need to pick a control volume. So I've been a little glib about picking the control volume. But what I'm going to do to pick the control volume is I'm going to pick point 1 to be at the top of the liquid here, and point 2 at the top of the liquid there. What that will allow me to say now is I want to go through and evaluate these different terms. So I can go through and look at delta H. So delta H is delta P over rho G plus delta V squared over 2G plus delta Z. And by picking the top of the liquid, I know that the pressure is atmospheric here. So that means I have, P atmosphere is P1 and P2 is P atmosphere. Okay, and so that delta P is going to be 0. So that'll mean delta P is 0. All right, and delta V squared, I know that V1 is about 0 and V2 is also about 0. So my delta V squared term is also going to be 0. All right, and that's because at the top here, my velocities are not moving very much, so I can neglect those. The total mechanical energy of those velocities is quite small. But I have a delta Z. That was given in the problem. That was 4 meters. So delta H just reduces to delta Z, which is nice. The other piece I need for my system demand curve is the head loss. The head loss, if you recall, is V squared over 2G times 4LF over D plus the sum of the minor losses. All right, and we said we're going to neglect minor losses, so these are 0 for this problem. Okay, but normally if I were to have picked the top of the liquid here, I would have to account for the sudden contraction into this pipe, any bends or valves that went along here. Okay, I don't have to do the pump minor losses. Those are included in the pump curve, in the pump performance curve, and then I'd have a sudden exit over here, any other bends or other pieces that I had over here. All right, so that's where this would come in, but for this example, I'm going to neglect it, but I'll write that here. If minor losses add here. Okay, so for example, that was contractions, elbows, etc. All right, so now I can write down my total system demand by combining this expression with this expression. So I'm going to get delta Z plus V squared over 2G multiplied by 4LF over D. Now, what I would like to do, since I'm going to equate the pump head and the system head to one another, I'd like to rewrite this in terms of the volumetric flow rate, Q. So recall that the volumetric flow rate, Q, is the velocity times the area, and so that, in this case, is equal to the area, is pi d squared over 4 multiplied by the velocity. So I can rewrite my velocity as 4q over pi d squared. Now coming back here, I can plug that in, and I'm going to need to square that guy. And so my system demand becomes delta z plus, well, that was the worst plus of all time. We'll fix it. Let's see, I'm going to have 1 over 2g multiplied by 4q divided by pi d squared multiplied by 4LF divided by D. So multiplying that out, I get delta Z plus, let's see, I get 4 squared, I'll just do it all out, is a 16 divided by 2G, and then I get Q squared, pi squared, D to the 4th, and then I have another 4LF divided by D. Okay, so 2 and 4 cancel, and 16 times 2 is 32. So let me scroll down here to my second page and add that on. I get delta Z plus 32 divided by pi squared. Okay, then I have Q squared. Well, I'm going to leave the Q squared out for just a second. I'm going to put it at the end. I'm going to do D to the 5th in the denominator. D to the 5th. I have a G in the denominator. I'll put a G down there. Let's see, have I taken care of all the denominator? I have the 2 canceled, the G, pi squared, D to the 5th. Okay, in the numerator now I should have an L and an F, and I'll put a Q squared out there. All right, then then my system demand curve is done. Okay, I could plug numbers in at this point, but I'm not going to. Okay, so I'm going to put, I could put numbers in. Okay, if I wanted to calculate what that is, but it gets a little, I think it's a little nicer to work it all out. All right, so now what I have to do is I have to equate my system demand curve to my pump curve. So look at that. My pump curve is given up here as H max minus BQ squared. So I come down here and I say H max minus BQ squared is equal to delta Z plus 32 divided by pi squared LF divided by G d to the 5th Q squared. Okay, so I want to stop and point out, now I'm treating the friction factor as a constant, right? I said that this was a constant here. Okay, if it wasn't a constant, this gets harder because look, I have a q squared here and a q squared here, so I'm going to be able to gather these, solve for q squared, and solve it by hand. But if not, if the friction factor is not a constant, then I have some complicated expression with a Reynolds number, and the Reynolds number has a velocity in it, which has the flow rate in it. Okay, so this becomes some complicated nonlinear expression that I'm going to have to solve for. So if I make this, not a constant, then what I have to do is rearrange this so that I have all my terms on one side. So I have some f of q equals 0, and then I use a nonlinear solver. Instead of f of q, that's maybe confusing. I can rewrite this maybe as some function phi of q equals 0. And then I would say use Newton's method. Okay, but in this case, so that's that case if I'm not a constant. But it is a constant, so I'm okay. All right, so now what I'm going to do is just do a little bit of algebra and rearrange. So I get on the one side H max minus delta Z is going to equal B plus 32 over pi squared LF divided by G d to the 5th, and all of this quantity multiplied by Q squared. So now I'm going to divide by this and take the square root. So Q is equal to, I have a radical, and I've got on the top H max minus delta Z, and on the bottom I have B plus 32 divided by pi squared LF divided by G d to the 5th, and I'm going to take all of that guy to the 1/2 power, to the square root. Okay, obviously I don't need the minus sign because Q is a positive quantity. All right, so plugging that all in, I'll let you do that on your own, but I'll tell you what I get. Hopefully I didn't make a mistake. I get 7.03 liters. Okay, excuse me, liters per minute. Is that what I get? Oh, yes. And I forgot to say that up here. This up here is B is in liters per, and it shouldn't be meters. That was wrong. It should be liters per minute squared. So that's what that unit is. Hopefully I didn't mess up my units. If I did, I'm sure someone in the class will help me figure it out, and then bummer, I'd have to remake the video. Okay, so now that I have Q, I know the operating flow rate. All right, so I know where this QOP is. That's QOP right there. So that's QOP is the right there. So how do I get H? Well, I have to go back and use either one of these formulas. I can either use H system or H pump. Where did I go? H pump right there to get my flow rate because they're both equal. So that's fine. So I would just take 7.03 liters per minute, put it in there, square it, and find that. All right. And if I do that, I find that the H of the operating point is 10.53 meters. Okay. So that will be this point right here. All right, so let me show you real quick. I have a Python notebook, so let me really quick open a new window here and show you this notebook. I didn't do a good job of pulling this up beforehand. Let me find it. Fluids, lectures, down here, pumps and turbines. Let me open a new notebook. Jupiter. Notebook here. And I'll pull this guy down. Alright, and let's open the example. Alright, and what I'm showing you here in this Jupiter notebook, so up here is boilerplate stuff, and I define a bunch of the constants. And here is the easy version that I just made for you, alright, or that I just did for you. So I define these two equal to each other, and I probably didn't even need to do that, because then I just come down here and find the solution. Alright, so this one's really easy. Down here, alright, and here's a plot of the easy version. That's why I made the functions, was for the plot. So I make a plot. Here I'm just plotting the demand curves, the supply and the demand curve, by making a linspace over some range of Q's. This isn't 0 because it freaks out if I'm 0. And you can see the point where they cross is the point that we solved for, and it's right there. Okay. Now, if I make the friction factor not a constant, here is a system where now I'm defining the friction factor in terms of the Holland equation, and now I have to do an f-solve. So I define some function phi, and I have to make them equal to 0, so I subtract the system demand curve over to the one side. This is the standard form, and then I solve this with some guess, and I happen to know a pretty good guess because I solved it with a constant, so it was around 7, and you can see that it makes a slight difference in where that goes. Of course, I had to calculate the friction factor, I don't know what the friction. If I don't know what the friction factor is, this is what I have to do. But I gave you a friction factor for this problem that was pretty close to the average of this one, so it didn't make a very big difference. Okay, so there you go. Oh, I didn't run this one. This guy runs, and that's an example of using a system demand curve and a pump performance curve to find the operating point. So with that, I'll close the video. Have a good one.